Chapter 6, this is one of the big distributions that we're going to look at. This is kind of rules the rest of our lives here for almost the rest of the course. Okay, interesting side note, if you ever want to go look up about, let's go Fisher, Roland Fisher, he had a lot to do with really fighting the movement about whether or not smoking cigarettes caused cancer. He was actually came down on the side that it didn't. But a lot of the work we're going to do from here on out is based on work he did. Check it out. It's kind of an interesting guy. So this is part of an old slideshow that I'd set up for years ago. I also see a couple of things that translate well. That's supposed to be equals. Okay, so this other textbook that I used to use used to talk about instead of frequency, relative frequency distribution, you used to call them density curves, and that's what we have here. Now, they don't give us, there's some things that are bad about this. They didn't give us a y-axis, that kind of thing. We have no idea how high these bars are, so we don't know that. But aside from all that, what we are looking at, we can talk about the shape, the center, and the spread. For this distribution, they're calling it close to symmetric. They're telling us here's the center, here's the spread. We'll talk about how to find that in a minute, and whether even we need to, but we will a little bit. Okay? Then, of course, there's all kinds of different density curves or relative frequency distributions, and they show us a whole bunch of different shapes here. The one that we're really going to look at a lot here is this bell curve. We're going to call it the normal curve. But there are these other shapes, and there are other distributions that are very useful in inferential statistics. This next set of slides is why I decided it was important to include this. The area under these density curves, or in other words, the probabilities, these areas always add up to 1, because it's a 100% chance of an event falling underneath that curve. And if we want to talk about specific areas, we can talk about, like they showed here. Well, in between this area and this area, there's a probability of an event of a number falling between, I don't know, it looks like what, 3 and 7 is 0.41, the probability of falling in that range. Notice area under the curve is always equal to 1. I just noticed that written out that way. Okay, and they tell us that the mean is always the balance point. So you can find the mean, so there's 0.5, well, I better not say that. There's a certain amount of the probability in this side will have to equal the probability in this side. And here's the important part here. With symmetric distributions, the mean and the median are always equal, or darn close to it. Okay, and what's nice about that, if we're starting to talk about probability again, or percentages of chance of it happening, 0.5, the probability of falling either side of the mean, which is the median, is 0.5. So that's useful. That'll be useful here in a minute or two. So in a skewed distribution, the areas aren't necessarily equal either side. Of course, they said for the median it is. Okay, in a symmetric distribution, the mean and the mean are the same, so those areas are equal to 1/2. And you can further subdivide that into the quartiles, right? You could say 25% of the distribution falls in each of these ranges, and if we knew what they were, we could use them for some calculation purposes. And in between Q, of course, you already know this from our IQR work, that 50% of the distribution will fall in there. So even though it's a relative frequency distribution, we know that it's all those same rules hold. So we spent last week, besides your exam, you were looking at simulating, trying to find probabilities of weird numbers that weren't just so straightforward. And I kind of we didn't even look at the whole binomial distribution thing. I think we're going to be able to get away without this. This came from chapter 6. I'm going to try to talk you through it because you're starting to use a little bit different terminology here that will help us later on. But we'll approach it from a simulation thing. I'm not going to do all the simulations, but at least you know where those came from. So they're saying here in this problem that According to some Heart Association article, 24% of patients who are hospitalized for a heart attack didn't fill their medicine that they gave them after 7 days after being discharged. So that's probably a problem, right? Issue. So suppose there's 12 people who've been hospitalized and then released, and then they're going to say, well, how many? Really, what we're interested in, this is where there's a little bit different information. What number? The random variable is the number of people out of the 12 who have not filled their medication prescriptions. Okay, and we know for any one person, we know that for the whole group of people, 24% of the people don't fill it. So how does that break down to be for different people? So what we're going to do is we're going to investigate some probabilities here and build a frequency table and draw a histogram. I'm going to show you what it looks like. You're not going to actually do this. And then the shape, and then we're going to talk about the mean and the standard deviation, then go beyond that. So what is the probability? So I mean, just so you know, I mean, what are the possible outcomes that could happen for 12 people? Well, 0 people could not fill their prescription, or 1 or 2 people could not fill the prescription, and we could go all the way down to all 12 of them did not fill their prescription. And what we really want to figure out is what's the probability, because they're looking for probability distribution, what's the probability that 0 people out of the 12 filled their prescription? Or how about what's the probability that 1 or 2 or et cetera, okay? So what all you know how to do now is to run a simulation for this, so why don't we? Now, we could use a random number table for this. You're going to see that I pulled some numbers from a website, so it's a little easier. And so let's come up with a probability model here. Since I know that 24% of people don't fill their prescription, I can say for any one person we can go 0, 0 or to 23, and that's 24 numbers. Because I'm using a computer website and not a random number table, I'm just going to be able to look at 0 to 23. So any number between 0 and 23 is going to be considered a person who didn't fill their prescription. And since I have 12 people, I'm going to look at 12 different pairs of numbers, or 12 different numbers, and then count how many of those people, how many of those numbers represent a person that didn't fill their prescription. So here's my first set of 12 numbers. I'm going to count up how many of these numbers are between 0 and 23. So 1, 2, 3, 4, 5. So there's 5 people that didn't fill their prescription. So what I can do is, if I wanted to do this all out, I could make it myself a list here, and I could do a tally. And so I had one set of numbers, one sample, one simulation showed me that 5 people didn't fill their prescription. So now I could do this again. I could generate 12 more numbers and keep doing this a couple 100,000 times, and then I'd have a nice picture. I'd have a nice estimate of what these different probabilities would be. Because remember, I'd have to total up my tallies and then divide by how many trials I ran. And that would be my probability distribution, and that would be based on simulation, just like we did last week. We don't want to do this that many times, and there are formulas that'll do this for you. And now what I'm going to show you next is everything all filled in using those formulas. So I went out and I used a spreadsheet to build this. There's many applets, and so here's what I was just doing right here. If we ran a whole bunch of simulations, it turned out that, or actually I used the theoretical, but we know that if we do many trials, we'll get theoretical values. There's a little less than 4% of the people there's little less than 4% of 4% chance or probability that 0 people will fill their prescription. Could be, and you'll see these numbers is increase. I mean, there's a 25, almost a 26% chance that 3 of the 12 people won't fill their prescription, and then it starts to decrease. And then what I did is, so this is my probability distribution. It's a relative frequency distribution. I hope you are making that connection. And then if I make a graph of this relative frequency distribution, I just graph these heights of these bars are the same as this. and my x-axis are these numbers. Now notice this is almost like a bar graph because it's like a category, right? So these are discrete numbers. This is a discrete probability distribution. So it's kind of this quasi mix between a bar graph and histogram. And we can use this by adding up the different bars. So if I wanted to know what's the probability of of 2 or fewer people in a group of 12 filling their prescription, I would have to add up those numbers. In other words, 0, 0.14, and 0.488. I'm sorry, wrong column. 0.03, 0.14, and 0.22, and I would add those up. Just so you know you already had done this. Back in the week 3 quiz, you were given this graph and you had to answer some questions about it. And this one version of it said, what's the percentage of people had blood pressure less than 120? So I would add up those two bars. That's 0.35 and 0.15. So 50% of the people had blood pressure less than 120. So going back to that binomial distribution, if I want to know what's the probability of the probability of between 0 and 3 people not filling their prescription, I could just add up those probabilities right here, right? I would add up those probabilities. Very similar. So this is a density curve. I hope you see that. I hope you're making that connection with those first couple slides. Is we're adding up those bars to get an estimate of the probability. Okay. Notice that this is kind of it's unimodal. This is a unimodal distribution. However, it's got a right skew to it, though not bad. I mean, it's not that right skewed, so it's starting to be kind of symmetric. Now, the other question they asked us back on that for the question part is, what's the mean of this distribution? So we're talking about right skewed. So we got the shape. The mean. What's the mean? The center. Well, you've done this already with the weighted mean, and that's all we're going to do. Here's the value, and here's the probability of it happening, or the percentage of people, or the frequency for that matter. And you can multiply all these numbers, and that's what I did for this x times p of x column. I just multiplied all those numbers, and I can add them up, and that is the weighted mean. And of course, these all add up to 1. So if I divide that sum by 1, I'm going to get the same thing. So there's the mean. Now the standard deviation is a little bit more involved calculation. We aren't going to go there. That's what it is. And for most of this work from here on out, you're going to be given the standard deviation, or it's a really easy calculation. The other thing we talked about in Chapter 3 was Chebychev's rule. And Chebychev's rule said, or theorem said, hey, at least 75% of the distributions fall within 2 standard deviations. So I subtracted that from the mean and I added that to the mean, and I came up with 95% of these numbers. 95% of the probabilities fell within 2 standard deviations, and for 3 standard deviations, almost 100%. So it certainly met Chebychev's rule, and because this is getting closer and closer to symmetric distribution, that's why these numbers are so much higher. So now we return to a uniform probability distribution, and this is right from the book, so you can go take a look at that if you want. And here, every class is the same probability of happening, and it's 0.1 as a matter of fact. We know this is height. We know that height because if we know the probability of every event happening is 1, and there's 10 events happening, 10 divided by 1 divided by 10 is 1/10. That's how they decided how high that was. If I only had 5 classes or 5 things, 1 divided by 5, that would make the bar 0.2 high, because 1 divided by 5 is 0.2. Okay, just so you know where that's coming from. But to answer this question, they're asking us, what's the probability they'll have to wait between 5 and 10 minutes for the next train? Well, let's see. Between 5 and 10 minutes. So you remember how I added up those bars in the last one? Well, between 5 and 10, well, we're seeing those 5 bars, all of them are 0.1 high, so and they're each 1 wide, so each one of these is 0.1 times 1, so that's 0.1, and we got 5 of them, so the probability of that happening is 0.5. What's the probability that we have to wait less than 2 minutes? Well, less than 2 would include 2 and include those 2 bars. So 2 times 0.1 is 0.2. Okay, so that's how this works when it's uniform. Pretty easy. The random variable is how long we'll have to wait, right? Okay, I think that's good enough. You'll have to answer a few questions, but in the book, they're pretty straightforward. So here we are, the normal distribution. It's going to rule our lives here for most of the rest of this course. It's a symmetric, unimodal. So that means the mean and the median are the same. We can talk about the probability of either side of this being 0.5. What else can we talk about this? If you've taken the SATs or the GREs, those are all standardized tests. That's, if you're not too far out of high school, you did the yes-back test or the NEASC test, not NEASC. I've already forgotten it. Those standardized tests, that's what they normalize them, they standardize them, and those are all normal curves. So we're gonna study this stuff in this next chapter. So our good friend Chebychev went on to found, well, it didn't take him long to realize that if you had a normal distribution, his rule could even be increased a little bit. And this 68, 95, 99.7 rule, our textbook calls it the empirical rule. Oh, I'm looking, that looks like a typo. Please excuse that. It tells us this, right? That 68, instead of 75% falling within 2 standard deviations, we can see that almost 68% of the data will fall within 1 standard deviation either side of the mean. 95, so notice 68, that comes first, 1 standard deviation. 95% of the data falls within 2 standard deviations, notice second number 2. And then, of course, almost all falls within 3 standard deviations. And these are rule of thumbs, and we're going to learn some other more exact ways to calculate this. But let's concentrate on the empirical rule right now. So I've got the next couple slides break that out and repeat what I've just said. And why this is important is, hey, if I have 68% of in the middle, in between plus or minus 1 standard deviation, notice it's using the population standard deviations instead of the S, and the mean instead of X bar, because we're talking about the population, not a sample. So how did they come up with these 16% out here? Well, if the probability is 1 for under the curve or 100 underneath the curve, and we have 68% in the middle, or 68%, we subtract that leaves me 0.32 or 32%, and since this is a symmetric distribution, we can cut those in half, and that's where they're getting the 16%. Okay, so if I were to ask you what percent of a normal distribution will fall more than 1 standard deviation below the mean, you're going to say, oh, it's 16%. Or how about more than 1 standard deviation above the mean? Well, same answer, 16%. Nice thing about symmetric distributions. Same deal with the 2 standard deviations. Okay, we're 2 standard deviations away, 95% in the middle. 100 minus 95 is 5. Cut it in half. We're getting our 2.5% either side. And lastly, if there's 99%, 99.7% in the middle, and we subtract that, we're going to get 0.3%. Or if it, as a decimal, remember that's 0.003. Move the decimal point over 3, 2 decimal places. And if we take half of that, that's where they're getting the 0.15. So again, this is a old slideshow that I created a long time ago, and as you can tell, I'm talking about the SAT costing 20 bucks. Now it's around 80, I think. So I think I made this in 2003, so back then. Anyways, so here's, in fact, back then there were only the two tests. There wasn't the writing portion, which is actually, it's gone back to just these two tests now. You can choose to take the writing portion for a little more money. So here's the mean, here's the standard deviation. Because these are standardized tests, we know the distribution of them is normal. And they're telling us that the center is 508 for the math and 505 for the verbal. Now, this is a little messy, but I'm hoping it helps you see this. Whenever I'm given a problem that deals with the normal curve, I'll always make a sketch. It won't be quite this neat, and you're going to see some of my work that's certainly not this neat, but it always helps to come up with it. I'll make a little curve, and I'll put the mean in the middle. Looks like this is the SAT math, because it was 508, and the standard deviation was 117. So what I did to get each of these numbers, as you can kind of see, I added the standard deviation to 508, and that's where I got the 625. Then I added another standard deviation to it and added another 117 to it. And I could have gone back to 508. I could have doubled the 117 and added the 508. Easier just to keep adding the standard deviation. Then going down, I subtracted the standard deviation 3 times, and then I kind of drew in this little sketch here to show you that, hey, 68% of people will score between 391 and 625, and that 95% of the people will score between 274 and 742. And then, of course, in reality, they don't record less than 200 or more than 800. But it is possible for people to do better than that or worse than that. So, advice: make a sketch, mark the middle, fill in your numbers. And this was the slide I just reiterated what I just talked about in that last sketch. Yeah, I didn't talk about this, that 50% score less than the mean. Now, I'd advise you to maybe copy this down or grab a screenshot as you're watching this video. What this is this is in between each standard deviation, the percent that fall in there. If I see one standard deviation either side of the mean is 68%, but half of it is 34. And then we know within 2 standard deviations there's 95%. So what I did is I said 95 minus 68, got that answer of what? 27. And then I took half of it, and that's how I came up with 13.5, because half of 27 fell in that range. And then, same deal, I took 99.7, subtracted the 95 that's in this range, cut the remainder in half, and that's where I got those numbers. And of course, we already know where the 0.15% came from. So if I were to ask you what percent or what probability, we could talk about probability, we talk about these as a percentage, what percent of all high school students this year, the year they took it, scored better than 391? Well, a couple of ways to do it. I could add up these, which adds up to 16, so better than 391, I said. So that adds up to 16%, or 0.16. And then since the whole area under the curve is 100 minus 16 is 84% of the students scored better than 391. If I wanted to know what percent of the students scored between 625 and 742, I could just use that number right there. Okay, this is a difference because this is a continuous, I don't know if I've said that word, this is a continuous distribution versus the binomial distribution. Those are discrete. So that's where we're going with this. We're going to come up with a way of dealing with discrete distributions, but not yet. So here's another problem we're going to be able to use the empirical rule for to answer. And it says police response time to emergency call is the difference between the time the call is first received and then when the patrol cars arrived. So they did some kind of relative frequency probability, it looks like, and they said the mean time is 8.4. There's a standard deviation of 0.17. So, make a well-labeled sketch I'm supposed to do. Remember what I said about making a sketch? And here's my first very exact sketch I'm going to make. So, I know the mean's 8.4. That goes in the middle. I'm going to draw 3 lines going up, 3 lines going down to represent the plus or minus 3 standard deviations. And then what I'm going to do is I'm going to add the standard deviation. So 8.4 plus 1.7 is what? 10.1. Let me get a calculator. Yep, 10.1. So it is 10.1, and just because I'm going to run out of room, I'm going to write this sideways. Then I'm going to add 1.7 again, and that's 11.8. And then I'm going to add 1.7 again, and that's 13.5. And then I'm going to subtract 1.7. That leaves me 6.7. And if I subtract it again, I get 5. I guess I need a calculator for that. And then I'm going to subtract 1.7 again and get 3.3. So, now what? They're asking us what's the probability, or what percent of the time it'll take between 6.7 minutes and 10.1 minutes. So 6.7 I'm noticing is 1 standard deviation below, and 10.1 is 1 standard deviation above. So this area right here is 68%. Or they're talking probability, so let's write it as 0.68. How about less than 3 minutes? Less than 3 minutes. It must have been a typo. What if I say less than 3.3 minutes? And actually, I'm kind of glad that happened. Notice how 3 minutes isn't one of my nice, neat numbers here. That tells me I need I can't use this empirical rule to solve it. I'll need another tool, which we're going to learn about in a minute. If you've read the chapter, you've already seen it. But if I say 3.3 minutes, notice that's 1, 2, 3 standard deviations below the mean. So 0.15%, or it'll be 0.0015 if we're dealing with a probability. How about more than 11.8? Well, I'm seeing that this is plus 2 standard deviations above the mean, right? Let me go to a blue. See, that's 2 standard deviations above the mean. So remember how in that little table I showed you that this is going to be 5% or 2.5%, I mean? And if we don't know that and we don't remember that, knowing that it's 2 standard deviations away from the mean, I know that 95% of the distribution will fall in there. 100 minus 95 is 5. Divide that by 2. I'm going to get 2.5%, or 0.025 if I want to talk about it as a probability. Then we throw this year that I did this, I was talking about percentiles, and a percentile is the percent of people that scored less than you. Since I'm talking about the 2.5th percentile, I'm looking for a number that has 2.5% less than that. And I know that at 2 standard deviations away from the mean, that cuts off the bottom 2.5%. So that answer will be 5. How about the 84th percentile? Well, if I know that 84%, I had to clean this up a little bit. I'm looking for the 84th percentile. So I know that there's 68% of the distribution fell here. And I know that 16% fell below that, because remember, if there's 68% in the middle, and 100 minus 68 is 32, half of that is 16. So down here there's 16%. And if we add that, what is 68 plus 16? I believe is 84. So that tells me what I'm really interested in finding is this probability, this area up here. Well, since this is symmetric and that blue area is 16%, that's also going to be 16%. So that's at the 84th percentile, which is 10.1. And that's the empirical rule. What we should do next is talk about how do you find numbers that are not on this nice neat table. All right, so same distribution, 8.4 is the mean. I've got a standard deviation of 1.7. I wanted to know what's the probability that less than 3 that the calls happen in less than 3 minutes. So I know it's going to be pretty small because it's outside of three. It's outside of 3 standard deviations, I believe. So that we know. But so the way to do this is to do a z-score. So the number I'm interested in is 3. The mean is 8.4. I'm divided by 1.7. So 3 minus 8.4 is negative 5.4. And I'm going to divide that by 1.7. So let's see, 5.4 divided by 1.7. That's a z-score of negative 3.18-ish. Then we need some way of finding that probability. Now, there's a lot of applet that you can use a table. Some books will talk about the table. Our textbook talks about using your TI calculator, and I'll let you read through that if you want. But if you don't own a TI calculator, you need another tool. So below this video, I'm going to have a linked another. It's a screencast at how to use this applet that's out on the web. It doesn't answer this question because I'm making this after I made that video, but we know this answer is going to be pretty small. Once you have watched those videos and you get some practice with that applet, why don't you try to answer this question? You can go ahead and post it in the forum. And that's one way I'll know who's seen this video or not.